Energy considerations in planetary and satellite motion. Let's say that we have a planet with mass capital M, then there is a satellite that is in orbit around this planet. And this is a circular orbit with mass M, and it has a tangential velocity v. We have a radial distance r between the two, and as you know from Newton's law of universal gravitation, the gravitational force points towards the center of the planet. Now, for this uniform circular motion, if we write Newton's second law, we can see that the gravitational force is the centripetal force, which is its mass times the centripetal acceleration, where the centripetal acceleration is given by v squared over r. And this is equal to our centripetal force, gravitational force, which is universal gravitational constant g, the product of the two masses divided by the distance between them squared. So from this equation, you can see that we can isolate mv squared. So mv squared over r is gmm over r squared. So if we get rid of one of the r's here, mv squared is gmm over r. And if I multiply this equation by 1/2, basically I obtain an expression for the kinetic energy of this satellite. So that will be 1/2 mv squared. G capital MM divided by 2R. So this will be the expression for the kinetic energy. Now, if I look at the total mechanical energy of this satellite, it will have a kinetic energy component plus a potential energy component. The kinetic energy is 1/2 mv squared. The gravitational potential energy is minus g, product of the masses divided by r, as we have discussed in the previous lecture. So now we have determined that the kinetic energy is G capital MM over 2R, and we also have the potential energy term minus GMM over R. So if I multiply this by 2 over 2, I can see that the total mechanical energy is minus G capital MM over 2R. And this result is true for a circular orbit. All right. So the total mechanical energy we can write as the potential energy, gravitational potential energy, minus gmm over r divided by 2. So it's u over 2. And the kinetic energy can be written as minus u over 2. And u is minus gmm over r. Okay. So how would these results be modified for an elliptical orbit if this is not a circular orbit, but it is an elliptical orbit? So the eccentricity is not equal to 1. Okay, so the total mechanical energy in that case is minus gmm over 2a. So we see that the radius of the circular orbit is replaced by the semi-major axis length a. So what is semi-major axis length? So if you have this elliptical orbit here, the semi-major axis length is the length of the longer axis, and the semi-minor axis length is the length of the shorter axis. Well, it's actually the total axis length is 2b, and total total major axis length would be 2a. So the semi-major axis length is a, and semi-minor axis length is b. So, okay, the expression that we have obtained for a circular orbit can be used for elliptical orbits as well if we replace the radius of the orbit with the semi-major axis length. So that's what we learn. Now, if an object moves from point A to point B, what would be the energy consideration for an isolated system? So if it has the same velocity at the 2 points, or if it's at rest at the 2 points, we just consider the potential energy change. So that's what we did in the previous lecture. So you can see if this object moves from point A to point B with no speed, it's going to have basically a change in the potential energy, and that's what we use to determine the potential energy as a function of r by defining the zero potential energy for the zero force configuration at r equals infinity. Now it's possible to have an initial speed for the initial orbit, so we would have a total mechanical energy 1/2 mv initial square plus the initial potential energy minus g capital mm over ri. And if we go to our final orbit, now we will have a final kinetic energy 1/2 mv final square minus g capital mm over r final. So if this is an isolated system, there is no energy transfer in or out of the system, then we will have this energy conservation equation. Let's look at an example. A space transportation vehicle releases a 470 kilogram communications satellite while in an orbit 280 kilometers above the surface of the Earth. A rocket engine on the satellite boosts it into a geosynchronous orbit. How much energy does the engine have to provide? Okay, so we have the mass of the satellite equal to 470 kilograms. Now, what is the meaning of being on a geosynchronous orbit? So, this is our geosynchronous orbit. In this case, we're basically going to say that we have synchronization with the Earth. So when the Earth completes one full spin, the object will have also completed a full rotation. So the Earth spins around its axis in one day, so the period of the rotation will be 24 hours. So that's the meaning of geosynchronous orbit. Okay. Now, we had an initial distance from the Earth's surface above the surface of the Earth. So it says, let's pay attention to this statement here. So what is the distance with respect to the center of the Earth? The initial orbit is at 280 kilometers above the surface, so 280 kilometers plus the radius of the Earth, which is 6,370 kilometers. So this object is released while in this orbit. So it's basically going to have no change in the speed while it's being released. All right. So our initial orbit is at a distance 280 plus 6,370, which is equal to 6,650 kilometers from the center of the Earth. That is 6.65 times 10 to 6 meters. Now, the geosynchronous orbit will have a final distance from the center of the Earth, r final. So these orbits are circular, we assume. Therefore, the centripetal force is the gravitational force. So in the final orbit, we will have mv square divided by mv square divided by r final. Okay, so this will be equal to g m mass of the Earth divided by all right, so this This is giving me a big RF square. So I can see that there will be a simplification here. So this mass m will disappear with this mass m, and also one of the radius terms, the radial distance terms will disappear, and I will find that v square is equal to g capital M E divided by r final. Okay, and this is equal to, because I'm in this orbit with a period of 24 hours, 2 pi r final divided by the period parentheses squared. So I find that the final orbit will have g m e t squared over 4 pi squared to the power 1 over 3 radial distance from the center of the Earth. So this will be my distance. Okay, now, so let me clarify this point here, that it has the meaning of being released is that it has an initial speed of 0 meters per second here, so it's released. Okay, so we can calculate this, our final, the radius of our final orbit. It's going to be 6.67 times 10 to the minus 11, 5.97 times 10 to the 24 times t square. The 24 hours, 60 minutes, 60 seconds squared, so that's conversion to seconds. This will be divided by 4 pi square, and then we have to take the power 1 over 3. So this gives us 4.22 times 10 to the 7 meters. Now, we want to calculate the energy that the rocket engine has to provide in order to achieve this. So what is the change in the mechanical energy? The final mechanical energy minus the initial mechanical energy. So the total mechanical energy, remember, is minus g, the mass of the Earth times mass of our satellite divided by 2RF, and initial is minus gmm over 2RI, but because of the minus sign this will become a plus, so this is plus g mass of the Earth, mass of the satellite divided by 2RI. So this will be minus 6.67 10 to minus 11 times mass of the Earth 5.97 10 to 24 kilograms times mass of the satellite 470 kilograms divided by 2 parentheses 1 over r final, because I put the minus sign here, this is going to become a plus now. 1 over r final, 1 over 4.22 times 10 to 7 minus 1 over r initial, 1 over 6.65 times 10 to 6 meters. So r initial I calculated here, if you remember. So this gives me an energy difference, delta E, when I perform this calculation, 1.9 times 1.19 times 10 to 10 joules. Okay. Now, there is another important concept here, which is called the escape speed. It is the minimum initial speed an object must have on the Earth's surface to be able to escape to an infinite distance from the Earth. Okay, so if we have an isolated system, if the object has the escape speed, it has the initial potential energy 1/2 mv escape squared. Potential energy is minus gmem over re because we're at the Earth's surface, and initial kinetic energy is 1/2 mv escape squared. This must be equal to the final potential energy. So we're going to an infinite distance from the Earth with zero velocity at the end. That means we will have, because we define the potential energy at infinity to be zero, this must be equal to zero. So this is the definition of escape speed. It's the minimum speed I need to have to be able to make it to an infinite distance from the Earth with a final zero kinetic energy. And this calculation basically shows me that V escape is equal to square root 2gme over re. So we can calculate this number to escape from the Earth. Okay, so let's look at an example. Escape speed of a rocket. Calculate the escape speed from the Earth for a 5,000 kilogram spacecraft and determine the kinetic energy it must have at the Earth's surface to move infinitely far away from the Earth. The spacecraft has a mass of 5,000 kilograms. We want to know its escape speed and we want to know its initial kinetic energy. Now the escape speed we have determined to be 2g mass of the Earth divided by the radius of the Earth square root. So this is 2 times 6.67 times 10 to minus 11 mass of the Earth 5.97 10 to 24 kilograms divided by the radius of the Earth 6.37 10 to 6 meters square root. So this gives us an escape speed from the Earth, which is, if you notice, independent of the mass of the spacecraft, to be 1.12 times 10 to 4 meters per second. So that's the minimum speed we must have to escape from the Earth. Now, what is the initial kinetic energy? Well, there I have the mass of the spacecraft being important because the kinetic energy is 1 over 2 m v escape squared. So this will be 1 over 2 times 5,000 times 1.12 10 to 4 squared. So that gives me an initial kinetic energy of 3.13 times 10 to the 11 joules. All right. Now, we have an important remark here. At a constant temperature, lighter molecules in the atmosphere have a higher average speed. So this we will find out in our study of thermodynamics. Having the same temperature, a constant temperature for all of the molecules, we will see that this will imply a lighter molecule will have on average a higher speed, and this speed can be greater than the escape speed. So who are the lighter molecules in the atmosphere? Hydrogen and helium. So these are very difficult to retain by the Earth's atmosphere because their average speed is greater than the escape speed, so they will be escaping to outside the atmosphere. However, in Jupiter, you can see that the escape speed is proportional to square root of the mass of the planet. So because its mass is much greater than the mass of the Earth, for example, hydrogen can be retained by Jupiter's atmosphere. So that's an important result. Another remark is that if we think about a black hole which has its mass approaching infinity, you can see that this escape speed is becoming very large. And when the escape speed is greater than the speed of light, basically we're inside the black hole. So if we set this escape speed equal to the speed of light, we find a radius given a large but not infinite mass of the black hole here. We find a radius that is 2g mass of the black hole divided by c squared. That's called the Schwarzschild radius. And this defines the event horizon. So what does it mean? If you go below this radius, even light cannot escape from the black hole. So we see that in the circular region defined by the Schwarzschild radius, it's completely black, so light cannot escape from this region, and that's called our event horizon. So beyond this, we have banding of the light as we approach the event horizon. So that's called, so where this starts is called the photon sphere. So that's an interesting application of the escape speed for the case of a black hole. All right, so in this lecture we talked about energy considerations in planetary and satellite motion. If we consider uniform circular motion, an object in a circular orbit around a planet with mass capital M, we see that its kinetic energy is minus its potential energy divided by 2, and the total mechanical energy of this object is minus the kinetic energy or plus the potential energy divided by 2. And if this is not a circular orbit but elliptical orbit, we have to replace the radius with the semi-major axis length of the ellipse. And when we change position, the radial position from point A to point B, if the system is isolated, the energy conservation implies that initial kinetic energy plus initial potential energy must be equal to final kinetic energy plus final potential energy. We have seen the application for changing the orbit of a satellite, where a communications satellite is basically released by a space transportation vehicle, while in an orbit 280 kilometers above the surface of the Earth into a geosynchronous orbit. And the geosynchronous we talked about, the meaning is the period is equal to 24 hours. So it's the period of the revolution of the Earth about its axis. So we look at the change in the radial position of the object. The satellite is initially at 280 kilometers above the surface of the Earth, and when it is in geosynchronous orbit, it's performing uniform circular motion. We see that the radial position will have a distance from the center of the Earth given by g met square over 4 pi square to the power 1/3, and this actually has to do with one of Kepler's laws we will see in the next lecture. By plugging in the numbers, we obtain the final radial position, and then we can just look at the change in the total mechanical energy, and the total mechanical energy is changing because the rocket engine is providing some energy into the system. The energy that we have to input is 1.19 10 to 10 joules in order to obtain this result. And then we have seen that if we take an object on the surface of the Earth, and if it has a minimum speed, escape speed, it will make it to an infinite distance from the Earth with a zero final speed. This value is proportional to square root of the mass of the planet and 1 over the square root of the radius of the planet. And the application was given for a rocket we can see that the escape speed, which is independent of the space of the mass of the spacecraft, is 1.12 10 to 4 meters per second. But the initial kinetic energy, because of the 1/2 m term here, does depend on the mass. And this escape speed concept basically explains why the Earth atmosphere cannot retain very light molecules, because in thermodynamics we will see that with the same thermal energy on average, these molecules will have a higher average speed exceeding the escape speed and making it out of the atmosphere. But for heavy planets, the chance of finding lighter molecules in the atmosphere is higher. For the case of a black hole, this escape speed can exceed the speed of light. So when the escape speed is equal to the speed of light, we have a certain radius of the orbit, which is called the Schwarzschild radius, and that defines our event horizon.